All right, we'll go ahead and get started. I'm sure there'll be some people still arriving, but hopefully you had a good break. And we're getting back into the swing of things. So I'm just going to start with some announcements now that we're completely online. Right, you're probably going to see more of me sitting in my office rather than in the classroom itself. But things to complete before the end of the semester, the first thing being the course evaluation. So I'd mentioned this before, but if you hadn't seen it, again, this is through the physics department itself. And so you have to go to physas.uga.edu and then /evaluations and sign in. And again, you should see this particular course. If you're signed up for more physics courses or an astronomy course or something, you're going to see those as well. So be looking for those. But this is due the end of reading day. I believe December 10th is the end of reading day. So if you're going to fill out this course evaluation, go ahead and do it early rather than late. I cannot reopen it after the deadline passes. So put that on your list of things to do just to check it off and make sure it gets done again before December 10th. The final project I had mentioned before we left for break, because I wanted you to be thinking about it over break, but today is the deadline to submit the survey. The link is on the ELC, but I will probably be posting another announcement just as a reminder to get it done by the end of today, to really choose your format, choose your topic, whether or not you're going to work with a partner, those sort of things. So the survey again is on the ELC. I'll post another announcement, but that part is due today. So if you get an email from me tomorrow, it's because you didn't complete this part and I want to know the direction that we're heading. Okay, so I know it's not due, and everything is not due until December 16th for the final project itself, but I'd like you to at least be thinking about which direction you're going to head. If things change in the future, you're more than welcome to just email me and let me know that you've changed topics, so you've changed methods of presenting it. That's perfectly fine. But I just want to know where we're headed. So today is that deadline again to submit the survey for what direction you're going to take for that final project. Okay. And if there were any questions, so there's a space on there, and I'll be responding to those of you who did ask questions regarding the topics or regarding the method or turning things in. I will probably be posting or creating an ELC Dropbox for this activity. Now, if you are going to be making a video and posting that, if the video is quite long, it might be difficult to upload. So I'm going to be posting several sort of directions if you're going to do that, maybe posting it to YouTube or something like that, and then sending me a link. So I'll have all of those instructions on the ELC with a Dropbox. And again, the deadline for the project is December 16th. However, you are more than welcome to turn it in early if you're working through it and you just want to get it done and wrapped up. Okay, so probably by the end of the week, I will start putting together that ELC Dropbox with all the instructions included in there. Okay. And again, stop me if you do have questions about it. The next thing is exam 4. I had mentioned before the break is coming up this Friday. So yes, everything will be online. It's already online anyway. Same procedure as the first 3. So you have an hour. It starts at our class time. A few minutes early, I started at 1:45. If you have questions during it, you're welcome to email me. So same procedure, nothing new other than topics. So I had already posted exam 4 topics as well as the equation sheet to the ELC in the content section, exam 4. So you can look for that now. But what it's covering is really where we left off from exam 3, which was electric force or static force from before. Now we're going to pick it up and really go all the way through circuits. So it starts with electric fields and then potential, which really got us into defining a simple circuit with a battery and a resistor. And those light bulbs are essentially behaving like resistors. So all of that work that we did with circuits is what we're talking about for wrapping up electricity. Magnetism, we went through fairly quickly because there's not a particular, say, formula or problems that we solved using magnetism. It was more of just a discussion of what creates a magnetic field, what does a magnetic field look like, and then we learned about electromagnets and how you can use electricity to create a magnet, right, which really led us into magnetic induction, which we talked about for a couple of class periods. So the magnetism chapter really is more conceptual in nature than the electricity, where we did do some calculations, right? We actually looked at some circuits and discussed different resistance and brightness of light bulbs, right? Talked about power. That's all included in there. Okay. And the last little bit that will be included on this exam 4 is really tying the worlds together. It's not too much conceptually, but it really is the last thing that we talked about before we left for break, which was to say that if you have a changing electric field and changing magnetic field, then you get light. So I put on there electromagnetism, but it's really just the basic principle of how we create light. And we're going to review that again as we start today. So hopefully today we'll get through talking about light in sort of a crash course, because you could talk about light for a long time, but we're going to do a quick crash course of what light is. But by including it on exam 4, all I really mean is that light is created by electric fields and magnetic fields. All right, kind of tying all of those concepts together then at the end. Okay. Same format as last time, so there'll be some multiple choice questions, true and false, and then some short answer. I think that's our perspective. Several students had asked me if they need to take exam 4, if they're happy with their first 3 grades. And so if you've looked through the syllabus, I do drop one of your exam grades. So if you are happy with your first exam 1, 2, and 3 grades, you do not need to take exam 4. However, you're always more than welcome to take it, as it's going to sort of boost the odds. If you do really well on it, right, then maybe you'll end up dropping one of your other exam grades. So I always say, take it, see what happens, but keep that in mind if you're thinking ahead and starting to study for exam 4. All right. Any other questions about that before we get started? Okay, if they pop up, please let me know, because it is worth talking about today.
Yeah, with the final, the final can only help your grade, you're saying?
Exam 4. So we don't have a final exam, it's just a final project. But exam 4 is technically not necessary, as I only take 3 exam grades.
Okay. But I mean, you just take it, and then if it's the worst one, it gets dropped?
Absolutely.
Okay.
Right.
Okay, right. Thanks.
Yeah, so you do need 3 exam grades, and if you've taken that, again, if you've had all 3 and you're happy with them, then you don't need to take this one. But I always say, do it anyway, just as a rule of thumb. Dana's asking about clicker questions. We're not going to do any clicker questions today. I want to get through the material fairly quickly, so that we can get to talking about black holes on Wednesday, as that was our most chosen topic in the survey. Right. So again, we're going to start talking about light, and this is really, the first couple slides are really what I mean to include on exam 4 in terms of light, because we need to have just the understanding of where it comes from. But then I want to spend today really talking about what is the nature of light, and how do we understand it and discuss it, and then what information can we get from it. Okay. So some of this may be review. You may have seen some of this information before in a previous science class, that's totally reasonable. But we want to have some sort of baseline understanding before we go on and talk about some of our astronomy topics, such as black holes, and some of you put exoplanets on there. Because to discuss our understanding of those concepts, we really need to know how astronomers have figured out the information that they figured out. Okay. So where we left off, right, and this is really what I mean for including on chapter or exam 4, is we left off talking about having electrostatic charges on a rod, right? And those charges create an electric field. And we talked about that in its static condition, right? You're just sort of holding it close to something, and you have a region that has an electric field pointed away from those positive charges. But now we've introduced that you move the rod around. And so by waving that rod, you're changing the electric field. And that changing electric field creates a magnetic field. Okay, so on this diagram here, okay, what it's trying to reproduce for us is a three-dimensional picture. Okay, hang on one second with this question. So on Wednesday, we're not going to be having a review. I do have office hours still tomorrow, and if you're looking for those, all the information's on the ELC. So I still have my normal office hours tomorrow if you have questions. And if you need to meet elsewhere, you can always email me and we can meet with questions about the fourth exam. But I'm going to take Wednesday to actually talk about black holes. We're going to start on our next topic. So it's the changing fields that create this light. But what this picture is trying to reproduce for us is a three-dimensional structure where you have the electric field, say, going in like an up and down direction and sort of shifting to the right, say X and Y direction. So that electric field is changing and it's moving to the right. That's the direction of the wave motion. So you can think about it like a wave kind of traveling as if you would think about like an ocean wave traveling to the shore. Okay. The magnetic field then is perpendicular to that. So you can think about it as sort of a forward and backward direction as it's oscillating, again, still moving to the right. And so it's the combination of that electric field and magnetic field that gives us our definition for a light, for light in general, but as we're thinking about them in terms of waves. Okay. So the fields themselves are perpendicular. Again, these images are trying to reproduce for us that three-dimensional picture. And I had mentioned to you before that light, in particular in a vacuum, because we're going to see kind of a different perspective a little bit later today, but in a vacuum travels at a constant speed. Okay, and that constant speed is 3 times 10 to the 8th meters per second. So if you've heard of this speed of light or heard that referred to, what it's talking about is that a light wave, or we can even think about it as a photon, is going to travel at a particular speed, which is constant as long as it's traveling through a vacuum. Okay. We ended class talking about needing to understand what astronomers are doing. And I said that we can work off this quote that light brings us the news of the universe, but we hopefully by the end of today, we'll just have some picture that astronomers are really getting information from the light itself. So that's why we need to have an understanding of what light is in order to know how do we get information about temperature or composition of a particular object, or even the speed, the motion of a particular object, right? Beyond just, right, light, of course, gives us a picture of something so we can see things that are out there. But obviously in thinking ahead, we're going to talk about black holes. The interpretation is that you can't actually see the black hole itself. And we'll get to that hopefully on Wednesday. Okay, so I had left you, sort of left you with a YouTube video of Dr. Quantum describing how light can behave like a wave or it can behave like a particle, and how strange things get at the quantum level. Okay, so if you want to go back and watch that, I think it's useful just getting us set up for the understanding that you can have both pictures of light. You can have a picture of light behaving like a wave, okay? And it's going to help us with our understanding of the electromagnetic spectrum that we're going to talk about soon. But you can also have sort of this picture in your head of light behaving like a particle, right? It sort of travels in a straight direction, a little photon, a little packet of energy, right? And it travels straight until it interacts with something. Both of those pictures, if you have one or the other, it doesn't matter, are still going to get you to the same concept. Okay, so reviewing that Dr. Quantum video hopefully will give you that impression. Okay, it's okay to think about one versus the other, and there's been experiments to show why it is that light behaves both as a wave and a particle. But we can work with both of those thought processes. However, we're going to start with light behaving like a wave. So if we work with this, right, electric fields and magnetic fields, right, and the way that they transverse and move through space, we can really start with a basic definition of something oscillating. So again, think of it just like a water wave on the ocean. If it's going to behave like a wave, then at some point it's going to crest, and at some point, so have a peak, and then at another point there's going to be a trough, right, where it's at its lowest point. Right? And we can describe particular properties associated with light behaving like a wave. So we can define the wavelength to be the length from peak to peak or trough to trough, right? You might have learned that condition. Or say starting point, and where do you come back to that same starting point? And the reason we need that information is there's a relationship between the wavelength and the frequency and the speed of the wave's motion. Okay, so the wavelength, we could say, is just peak to peak, the distance, right? So as this wave is traveling, right, you could think about measuring the wavelength from peak to peak or trough to trough. The amplitude is the height of the wave, and that could be either from some 0 point to the peak, but it could also be from that 0 point down to the trough, assuming that it's going to reach the same amplitude as it continues to propagate. So it doesn't matter if it's up or down. We're just thinking about it as an amplitude. The frequency describes the number of waves that are passing. So you can imagine setting up an experiment to where you're watching, say, a water wave pass you by, and you're sort of ticking a certain amount of time. How many troughs do you see pass? How many crests do you see pass? Right, the number of wavelengths that pass in that particular amount of time. And the period would be the time just to complete one of those. So having one full wavelength pass is a particular time period called the period. I think we've already described period in relation to other concepts. But we want to look at that, how these descriptions give us information about the speed as well. So relating it to something that we know, I like to take light as a wave and relate it to sound. Because if you can keep those principles in your mind, it really does help understand light. So with a sound wave, if you've heard of something like whether or not something is loud or soft, or high frequency or low frequency, or high pitch or low pitch, right? If you're thinking about sound itself or music, then what we're talking about, if we talk about loud sound, okay, versus something that's quieter, you're talking about the amplitude itself. Right? So essentially, how large are the waves, right, in terms of an amplitude here, distance away from some 0 point. Whereas if you're talking about pitch, so you're talking about whether it's high pitch or low pitch, right? Then what you're looking at is you're looking at the wavelength itself. Is that wave stretched out? Right. It'll take a long time for that wave to pass you. Okay. Or is it more crunched up? What's the frequency of it? Okay, so the short frequency here, or I guess I should say high frequency short wavelength, means that you have more waves passing you in a given amount of time. Right? It's sort of a stormy condition on the ocean, versus having that low pitch, right? You sort of very long time periods between waves passing. So if that helps you, right, think about those different properties on a very basic level for waves, I think that's a good thing to go to. Okay? Because what we're going to be talking about, or what we're going to be using as we describe electromagnetic waves or light waves, right, is the relationship between, again, wavelength, speed, and frequency. So with light in particular, it's moving at a constant speed. So we know what it is. Here I have it written in kilometers per second. Okay, so 300,000 kilometers per second. And that's always true as long as we're talking about light. Speed could be different if we were talking about sound, or if we were talking about water waves, right? Or waves on a string or something like that. The speed would be different. But for light, it's going to be that 300,000 kilometers per second. And there you can see the relationship between wavelength and frequency. And why we need that information is because light can be composed of all different ranges of wavelengths or frequencies. okay, whichever one you are thinking about. So the spectrum itself here is shown with frequency on the top axis and wavelength on the bottom axis. Okay. So again, if you're thinking about high frequencies, you're thinking about high pitch, low frequencies, low pitch, right? And in terms of wavelength, then you'd have very short wavelengths at high frequencies. And you're looking at that relationship there, the wavelength 10 to the minus 12, right? Very small number with a very large number for the frequency. And then you have on the opposite end, right, you have lower frequencies and very large numbers for wavelength. Right? And the radio really could continue on, right? They're just showing order of magnitude, right? 10 to 100. You could really continue that on, but we're just sort of cutting it off to give us some ending point for those regions. Okay. And so if you look at these regions, what we have at the high frequency region is we have very energetic light. So we've talked about it before. We've talked about gamma rays and that they're dangerous, right? And you don't want to be exposed to them. And the reason being is because the energy that's associated with having these very short wavelengths or these high frequencies. There's a relationship with energy here. So you could put energy on this graph, and this would be the high energy region. You can step into the X-rays, right? And now we are increasing our wavelength, decreasing our frequency, right? But still dangerous, right? Still high energy in terms of what we've discussed. Ultraviolet is next, right? And this, we've looked at our regions. You can go back and think about when we were talking about the atmosphere and the light that comes through our atmosphere. I showed you a similar picture to this, but showed you that there are a small region of the ultraviolet that does make it through the atmosphere. That's why we use sunscreen. But for the most part, our atmosphere blocks most of this very high energy light region. The visible portion is really just relevant to us, right? This is what we can see. So if you've heard the term white light before, white light is composed of the entire rainbow of colors here, which are defined for particular wavelengths, right? So that Roy G. Biv makes up all of the white light. And that's the visible portion, which is really the only thing that we can see. So we can't see ultraviolet, X-rays, gamma rays, right? Or the longer wavelengths that I'm going to keep talking about. We can only see that visible region. So it's really, really small what our eyes can actually detect. But that's what we're thinking about when you sort of see a picture of something, right? Or see something in front of you. We're viewing things from that visible portion. As you go to, again, lower frequencies, higher wavelengths or longer wavelengths, we're getting into the infrared now, and you can't see it, but we're going to see the importance of the infrared region. You go even longer, you're talking about microwaves, right? And now we're getting into the region of radio, and you're kind of on this border between things like cell phones, right? Television, radio, communications, right? All of that is at very long wavelengths, very low frequencies. And there's a reason for that as well, but we won't get into that today. So the reason we need that whole electromagnetic spectrum is to understand when we talk about astronomers are going to observe light, right? Well, what particular light are they going to observe? And how do we use that? So I'm going to focus first on infrared, okay? Because you can set up a detector to be particular to this portion of the spectrum, okay? Just the infrared spectrum. And we can't see it, right? We can't, but some animals can. And in particular, you can create devices that can measure that infrared region of the electromagnetic waves. But what you're measuring there is temperature. So as I had mentioned before, one of the things that astronomers are getting from light, right? Well, if they're measuring in the infrared region of the spectrum from some particular object, right? If they're looking with an infrared filter or an infrared detector, what they're measuring is they're measuring a temperature. Okay, so animals emit in the infrared, right? Clearly we are warm beings, but besides just animals using it, right, we can create or design ways to use infrared vision. Right? So we've heard of night vision goggles or things like this, right? It's acting on the same principle, right? You are using a filter or a detector in particular to measure the output of heat in order to see, say bodies that are moving. So what you see in this picture are the things that are more illuminated or more white, are hotter than things like, if you look at this picture, the sky is very, very dark, right? Implying that it is colder in that region. So your detection device is creating a scale sensitive to say human temperature. So infrared region, you're really looking at measuring temperature. Ultraviolet, and I'll go back for a second so that we can look where the ultraviolet was. So if we go back to the ultraviolet, now we're going to the other side of the electromagnetic, or the other side of the visible spectrum, to the higher energy, okay, rather than the infrared. But in the ultraviolet region, right, again, we can't see it, but some animals can. And it's useful, and I like these pictures because they're giving you an idea of how things can look different just based on limited vision, right? So to us, right, you might see flowers that look like this, right, in these two particular pictures. The visible light would be if we were to go and take a picture and look at it. But if you put an ultraviolet filter on it, what you see is you see kind of like a bullseye towards the center of the flower itself. There's like this darker region on those petals leading you to essentially where the pollen is. And so pollinators have ultraviolet vision, have some ultraviolet filters that enable them to see where the pollen would be. Kind of a cool idea in terms of animals using other wavelengths besides what we can see. But as that light is traveling, right, besides those different wavelengths, it interacts with things. So this is where we need to have our distinction between light behaving like a wave or a particle, right? Stick with whichever one works for you, right? But as that light is traveling, it's traveling at a constant speed, right? And it travels straight until it interacts with something. So the interaction is the tricky part with what astronomers are really trying to deduce. And so I want to go through these fairly quickly, right? We're not going to go into too much detail or the physics of light in a lot of detail. But I want you to be able to see what we mean by looking at whether light is absorbed or scattered or reflected or refracted. Okay, different terms for how we might use the light. Okay, so we have this picture of the whole spectrum, and we're going to focus first on talking about how it's used. Right? In particular, where's the light coming from? So imagine that you have the light being generated by a particular object here, shown as a light bulb, which is a good place to go since we've been talking about electricity. And what astronomers use or measure is the description of both luminosity, but also brightness. And those two terms mean different things. And so I want to focus on that in particular because we've talked about we started class talking about energy, right? But we didn't get too much into radiant energy, which is really a discussion of luminosity. So whatever it is that's generating the light itself, right? However it's being created, the energy is dissipated as light, and it's radiating away from that particular object. I believe we've mentioned before, as we went through and talked about energy itself in different forms and different magnitudes and scales. I had even mentioned to you that the sun's luminosity, what that is it's really a measure of how much energy, right, in terms of light is being released from the entire surface per second. Right? So you're thinking about light as an energy form coming from the object. Once it gets to us, now we're talking about the brightness of it. So clearly, if you were to go and sit right next to the sun, it's going to be way brighter than it is at our distance. So the brightness itself is with respect to how far away you are, the distance from the source itself. And I only bring it up because the relationship between brightness and luminosity behaves as a 1/r squared again. So now we've seen this several times this semester, right? It's really a law or principle that holds through many different forms of physics, but in particular here in relation to luminosity and brightness as well. Right? So another inverse square law there in terms of a relationship. But again, this light is generated from a particular object, right? What we're going to start talking about is measuring that energy in terms of a brightness, right? But let's look first at what happens when that light is reflected, right? So remind yourself that something must generate the light, and then we're talking about the brightness of that light itself, or what can happen with that light once it leaves the particular object. But reflected light is really just the light that can bounce off of a particular surface, and this can be in full. So if you think about a reflection like you're looking in the mirror is having majority of the light. We usually generalize to say 100% of that light will come in and bounce off of that surface. Right? So all of that light will bounce off. So that's the interaction, right? It's really a bouncing of that light, a changing of direction of that light wave itself. If it's not perfectly reflective, right? If it's not a mirror in your bathroom, then some of it could be absorbed, but there's still going to be some portion that's reflected. So it might not be all of the light, okay, but majority of it will still be reflected off that surface, depending on what the surface looks like. Right? So when we talk about observing things, in particular objects like planets, even the moon, right? Even the moon is on there. When we talk about observing them, what we're really doing is we're observing reflected light. So these objects themselves are not generating light in the visible portion, right? If we go out and we look through a telescope and we see it with our own eyes, what we're seeing in the visible portion is we're seeing reflected light from the sun, which is kind of interesting because some of you may be aware, but if you're not, look for it the next time the moon is out. I believe we just passed a full moon, so wait for it to come. But if the moon is in a different phase, so say you're getting close to a new moon phase, which is usually when the moon is relatively dark, there are times where you can see it up close to the horizon, and it might look something like the second picture here, where it's really, really dark, but you can still see the moon. It's not that you are observing the reflected light from the sun, which is shown here as this very, very thin crescent shape. Okay, that's the reflected light from the sun. Instead, what you're observing, so usually this is at dawn or at dusk that this would be observed, but what you're observing is you're observing the sun's light reflected off the earth onto the moon and then back to us. So multiple reflections going on to create that darker appearance, right? Even though we say the moon phase is a crescent, okay, you can still see some other portions of the moon just from the reflected light off of the earth itself. Okay. So again, the earth is not a mirror, but it reflects some of that light back onto the moon's surface, and we can even see it then too. So the reflected light is really just the bouncing of light itself. Scattered light, right, so we've talked about reflected, but scattered light, again, is something that we are familiar with, mainly because it explains why the sky is blue and why sunsets are red. So the scattering itself is because the light can come through the atmosphere and it's interacting with particles, right? So now, instead of having just sort of a surface that it's interacting with, it's going to interact with particles or molecules, atoms in the atmosphere itself. And depending on the relationship between the size of that particle, right, so fairly small if we're talking about molecules in the atmosphere itself, and the wavelength of light, it can scatter particular wavelengths. So again, not the entire electromagnetic spectrum, but wavelengths where the relationship is close, right? So small particles, short wavelengths, right, can get scattered. So when light comes in from the sun, it's coming in with all the colors, right? Roy G. Biv, but in the visible portion. But the blue light is scattered because of the atmosphere itself. And it scatters in a way such that we see, it appears to be blue in the sky. Whereas the green and the red can come through, they don't interact as efficiently with those particles themselves. Okay. With a sunset, kind of a similar picture, except now it also has to deal with how much atmosphere the sun's light passes through. So at sort of a high noon picture, right, the sun is overhead, there's less atmosphere for those particles to interact with, right? So yes, you get some blue scattering, right? But by sunset, the light from the sun has to travel through a lot more atmosphere, right, at a different angle. And as it travels through that, most of that blue light scatters out of the atmosphere itself, to where the light that we're seeing, sort of illuminating, is the red picture, kind of the leftover. The longer wavelengths are what remains. So light can come in and it can bounce off of objects in a reflected way. It can come in, it can interact with particles, right, and sort of scatter particular wavelengths, depending again on which portion of the electromagnetic spectrum we're looking for. It can also refract, and we're familiar with this, but refraction is interesting because what happens is light comes into a material. So think about light traveling in particular through a prism. So white light goes into glass. Instead of just traveling through vacuum or air, right? It goes into a material, a transparent material in this case, right? Glass or plastic or things like your window. Right? But that light can go through a particular medium, and what it's doing is it's actually slowing the speed of light. And remember, there's a relationship between speed and wavelength and frequency. So if I change that speed of light as it passes through a different material, that light is going to bend or separate. So this prism, the reason we get a rainbow as that light passes through a prism, right? Or the reason we see a rainbow is because that light goes into a water molecule, or a thing that behaves like a prism. It might reflect internally, right? We're not going to worry about that part, but it refracts or it bends when it comes out, and that refraction, the amount that it bends depends on the wavelength. So we see that red bends less, right? It ends up at the top there, and that purple bends the most. And so as you go through Roy G. Biv, right, you get that whole rainbow forming as the light is passing through. So again, showing us evidence that sunlight is composed of white light, or all of the colors of the rainbow combined, but we can use different materials to separate those wavelengths, to split them up. And this is really important to astronomers as well, not just creating beautiful rainbows, but we're going to see how we can use that separation of the wavelengths to get even more information. All right, so we have reflected, light can bounce. We have scattered, light can essentially come and interact with a particle and scatter away. We've talked about refracted, in which light can bend, right? And the last one, which is also super interesting but complicated, is that light can be absorbed or emitted. And so we'll look at both of those. So if light is coming into a material now and it's getting absorbed, right, well, we need to know what is the material, what actually happens when light, think about it as energy, when light gets used up. Okay. So this picture here, keep it in the back of your mind for right now. But what you see is you see that whole rainbow picture. Okay. So think of this as the visible portion of the electromagnetic spectrum going from red to blue to violet. And what you notice is you notice those little black lines, right? Well, those little black lines are essentially absorption from a material such that it's eliminated that particular wavelength. Right? So the red region of the spectrum is not just one wavelength, right? It's a range of wavelengths. Just like orange is a range of wavelengths, yellow is a range, green, blue, violet, right? You have a range of wavelengths there. And as that light passes through a particular material, some of it can get absorbed depending on the material itself. So these little black lines are like someone has taken pieces of the electromagnetic spectrum out and kept them. It took that energy, it took that wavelength away. Okay. So how does it do that? Right. Well, we have to know something about the material itself, which really is we have to know about atoms again. So I know this is just a review because we've talked about atoms several times this semester, right? But we have a nucleus with those positive charges and the neutrons, and then we have this cloud around it with the electrons. And when light comes in, the first thing it can interact with is the electron itself, or electrons in the cloud. And so it depends on what those atoms or molecules look like. Right? So if we're imagining this and we're thinking about just using our atmosphere as the first example, right? The oxygen, say the oxygen atom and then putting it together to create an element O2 is going to have a unique structure of electrons surrounding it, which is going to tell us something about what might happen if light comes and interacts with one of those particular electrons, say in the outer valence region or something like that. So we need to know that atomic structure. We need to know what it looks like. And what we're going to focus on first is just thinking about hydrogen, and we might get back to it later, but in particular because hydrogen makes up most of the universe. So hydrogen being a very dominant atom, right, is why we focus on it a lot of times. But what we've learned or what we've talked about is we've talked about the electron, okay, the electron that surrounds, right, one proton, one electron. There's different energy levels for where that electron could be situated. Right? And so that's usually what's described as these n equals 1, 2, 3, 4, right? And then they have n equals infinity state. Right? Well, that electron can move between those energy levels. And in order to move between the energy levels, right, it either has to absorb energy or emit energy. Right? So if it emits energy, it's going to drop down. If it absorbs energy, it's going to jump up. Right? So I like to compare this to just thinking about the bookshelf example that we used for potential energy when we started class a long time ago. But a similar idea, if you are going to pick up a book and move it to a higher shelf, you have to put some energy into it. Right? If the book falls down on its own, it's taking energy from gravity, or it's absorbing energy from something else. Similar idea with an electron in these states, energy states. So if it absorbs some of that energy, it can move to a higher energy level. If it releases some energy, it'll fall to a lower energy level. So with hydrogen, if you look at the energy or the difference in energy levels, moving from something like n equals 3 down to n equals 2, or n equals 4 down to n equals 3, right? If you look between those energy levels, there's a particular amount of energy associated with those regions. Think about it like bookshelves. So associated with that energy then, right, if they each have their own particular energy going from 3 to 2 or 4 to 2 or 5 to 2, right, 6 to 2, all of these are defining what we call the Balmer series. But with that particular amount of energy comes a wavelength of light. So if the electron were to fall between those energy levels, it would emit energy. Right? So we get this emission of light. So we're talking about how do we create light in general? Well, it turns out, right, that atoms themselves can emit light. They can emit electromagnetic waves, right, which have a particular energy associated with them based on wherever it's falling from, right? If it's falling from a higher energy level down to n equals 2, right? Maybe it's in the Balmer series. We can go back and look at that picture. Maybe it's in the Lyman series. Maybe it's a higher energy, something ultraviolet versus something visible light. Right? But you can create the whole electromagnetic spectrum just by looking at emitted light from electrons dropping down in terms of energy levels. If you're going to drop down, you're going to emit some energy. So it gets us back to absorbing, right? We talked about light coming in and interacting with the material. If that light comes in and is absorbed by that electron, the electron grabs all of that energy, then it has enough energy to jump up. Right? It could jump completely out of the atom, ionizing, right? Or it could just jump up between, say, energy level 1 to energy level 2, as it absorbs that energy from the photon itself. Sometime later, it's probably going to fall back down. Sometime later, it's probably going to emit that energy again as a photon. Yes, but momentarily it is absorbing that light. So as we go back to that picture that I kind of started with, one thing that astronomers look for is they might use all of these principles together, right? Look at the light coming from a particular object, pass it through a prism so that we can see the entire visible or optical visible portion of the spectrum. And then if you get that picture and you start to identify wavelengths associated with each of these particular black regions, something that was absorbed out of the spectra, you can start to identify different molecules or different elements. So you're getting composition information from absorption of light. Right? If this particular black spot refers specifically to an energy level for hydrogen, then we have some hydrogen being absorbed out of the light itself as it reaches us. So it keys to, well, there's probably hydrogen in that star because I'm getting a whole bunch of these really big black absorption features at a particular wavelength associated with, say, the Balmer series, the Lyman series, with hydrogen itself. So you're getting a lot of information. In particular, let me go back to the pieces that we've used. How do we take that light? How do we take that light and use it? Right? Well, we need to know how it interacts first. So it can reflect, it can refract, it can scatter, it can absorb, and we can use all of these together to get us into thinking about how we get temperature. So I'm not going to go too much into the detail of temperature, speed, and composition. I just want you to know vaguely sort of where it comes from. Temperature, we've kind of referred to, right, is really looking at infrared. So you can think about creating a device that would specifically measure infrared, which is essentially giving you temperature. We can use this idea of absorption, right, looking for where molecules or atoms have absorbed light, taking it out of the electromagnetic spectrum, to look at composition. And then we'll get back to speed a little bit later if we talk about exoplanets, right? But it's another piece that we can get from the light itself. Okay, so I know this is kind of like a crash course in light, but the last thing that I wanted to mention is that astronomers are really using all of the electromagnetic spectrum to get all of that information. Okay, so I had already mentioned to you before as we were talking about a picture of the sun, but I like this picture from NASA because it really gives you that idea that when you look at a different wavelength, if you use a particular filter, you're going to get different information. So we were talking about it with respect to looking at, say, star spots or sunspots, right? And then referring to them in terms of looking in the ultraviolet, you're really seeing that almost that magnetic field as it follows those plasma trails. So it's kind of cool to think about that you're using the entire electromagnetic spectrum to get all of that information and really study some of that in more detail. But the main piece as we kind of move forward into thinking about some of our astronomy concepts is that astronomers need telescopes to do this. Right? And so I start this discussion really by just thinking about what the main function of a telescope is, right? And I know that class is sort of wrapping up, but I'll go ahead and give you some of our ideas, and we'll start here on Wednesday, right? That you might be thinking about or you can translate what you were thinking about into one of those. But we'll start on Wednesday talking about magnification, what we call light gathering power, and resolution. And I want to leave you with thinking about how would you rank those in terms of importance. Okay. So again, when we come back on Wednesday, we are going to start talking about black holes. We're not going to do a review session for this particular exam. The information is online, but start here and be thinking about how you would rank those in terms of importance. All right, so I'll go ahead and stop, but if you have questions, let me know.